A bumblebee looks like a creature assembled from parts that should not work together. A round, furry body, 6 small legs, wings that seem far too short and thin for the job. Then it lifts off, hangs in one spot, turns almost on the spot, and disappears over a hedge carrying a load of pollen. According to a famous story, the laws of aerodynamics say this should be impossible. The story is usually followed by a cheerful line. The bumblebee does not know it cannot fly, so it flies anyway. Nice motivational quote. Bad physics. No law of nature has ever forbidden a bumblebee from flying. The insect is not breaking aerodynamics. It is using a version of aerodynamics that early calculations did not describe very well. The mistake was a bit like measuring a helicopter as though it were a small airplane, then being surprised when the numbers look wrong. One commonly cited source of the myth is a 1934 book called Le vol des insectes, or The Flight of Insects, by the French zoologist Antoine Magnan. In its introduction, Magnan described calculations made with the engineer and mathematician André Saint-Laguë. Using the aerodynamic ideas available to them, they reached the conclusion that insect flight appeared impossible. The exact route from that passage to the modern bumblebee legend is messy. Other versions involve an engineer making a calculation over dinner. We cannot prove every retelling came from the same place. Still, the basic error is clear. Take the area of a bumblebee's wings. Estimate its speed. Treat those wings like small, rigid aircraft wings moving steadily through the air. The calculated lift may be too low to support the insect's weight. On paper, the bee drops. But look at a real bumblebee for half a second. Its wings are not fixed to the sides of its body. They sweep back and forth, change angle, twist, bend, and reverse direction. Depending on the species and the situation, they may beat roughly 150 to 200 times per second. At that speed, the wings are a blur, and the air around them never settles into the smooth, steady flow assumed in a simple airplane calculation. That sounds like a technical detail. It is the whole case. A conventional airplane wing gets lift because air flows around its shape as the aircraft moves forward. The wing pushes air downward, and pressure differences help produce an upward force. If the angle of attack becomes too steep, the airflow can separate from the wing. Lift falls, drag rises, and the wing stalls. A bumblebee repeatedly uses wing angles that would look alarming on an airplane. Yet its wings do not simply stall and stop working. During each stroke, the sharp front edge of a wing helps roll the air into a rotating structure called a leading edge vortex. This vortex creates a region of low pressure above the wing and can keep lift high even at a large angle of attack. You can see this in smoke visualization experiments. A bee flies through a thin cloud of smoke, while high-speed cameras record how the air curls around its wings. Instead of a neat stream passing over a miniature airplane wing, researchers see vortices forming and moving with the flapping wings. The bee is constantly making, using, and shedding these swirls of air. The vortex is not a magic bubble permanently glued to the wing. Its shape and strength change through the stroke. The wing accelerates, sweeps, slows, rotates, and reverses. Air disturbed by one movement can affect the next one. Researchers use terms such as rotational circulation, wake capture, and added mass effects to describe parts of this unsteady process. The exact contribution of each mechanism depends on the insect, its speed, and what maneuver it is performing. There is no single trick that explains every moment of flight. Now shrink the whole problem down to bumblebee size. Air does not feel quite the same to a small wing as it does to the wing of a passenger jet. Engineers describe this using the Reynolds number, which compares inertial forces with the effects of viscosity. A large, fast aircraft operates at a very high Reynolds number. A tiny insect moving through air operates at a much lower one. The air has not become syrup, but viscosity matters more at the insect scale. A flow pattern that works well around a Boeing wing cannot simply be reduced with a photocopier and expected to work around a bee wing. Size changes the balance of forces. This is one reason early aircraft-based estimates were so misleading. There is another detail hidden in that wing blur. A bumblebee appears to have two wings on each side, a forewing and a smaller hind wing. During flight, tiny hooks connect them so that they work together as a broader aerodynamic surface. Then the surface flexes. Researchers have tested that flexibility in a very direct, slightly rude way. They stiffened the wings of living bumblebees. The altered wings still moved, but they could not deform normally under aerodynamic load. The bees with naturally flexible wings produced more vertical force and showed better load-lifting performance. In another set of experiments, flexible wings also helped flight stability in turbulent air. So the wing is not a rigid paddle. Its shape changes passively as air pushes against it. The insect does not need a separate muscle to control every millimeter of bending. Part of the wing's response comes from its material and structure. That saves control effort, and it can improve performance. A thin sheet of insect wing is doing useful mechanical work simply by not being perfectly stiff. A pollen basket makes the challenge more obvious. A worker can return to the nest with yellow or orange clumps packed onto its hind legs and nectar stored inside its body. The extra mass changes how much force the wings must produce. Bumblebees can respond by changing their wing motion, including the stroke amplitude, rather than relying only on a dramatic increase in wing beat frequency. In laboratory lifting tests, some bumblebees have generated enough vertical force to carry loads approaching their own body mass. Results vary with species, body size, temperature, and the way the test is performed. So this is not a universal bumblebee specification. Still, it is a useful reality check. The supposedly underpowered insect has aerodynamic capacity in reserve. A pressure chamber produced an even stranger demonstration. Researchers collected alpine bumblebees that normally lived at high elevations and gradually reduced the air pressure around them. All of the tested bees could hover under conditions equivalent to about 7,400 meters above sea level. Two continued at simulated elevations above 9,000 meters, slightly higher than Mount Everest. They were not flown over the summit, of course. Temperature, wind, and oxygen conditions on a real mountain are more complicated than pressure alone. The experiment measured aerodynamic performance in thin air. The bees compensated mainly by sweeping their wings through a wider arc, not by beating them enormously faster. Now put the bee back near a garden fence on a windy afternoon. The air behind leaves, stems, and branches is full of uneven gusts and rotating wakes. For an animal only a few centimeters long, a small eddy can shove the whole body sideways. High-speed recordings show bumblebees rolling, pitching, and correcting their paths in disturbed air. Numerical studies also suggest that strong turbulence may leave the average force over many wing beats surprisingly similar, while making the moment-to-moment forces far more variable. In plain language, the bee can still produce enough lift overall, but the ride becomes rougher. It must correct the wobble, not always instantly, of course. Some very fast disturbances are partly absorbed by the bee's body and flexible wings before its nervous system can react. Slower deviations can be corrected with changes in wing motion and body angle. This mix of passive stability and active control is one reason engineers study insect flight when designing very small flying robots. The bee is not indestructible. Wings wear down as they strike leaves, scrape against surfaces, and simply accumulate damage over a worker's life. Experiments show that worn or damaged wings can reduce acceleration and maneuvering performance. A bee may still fly, but tight turns and emergency escapes become harder. There is no force field around the vortex. Damaged hardware is still damaged hardware. This brings us back to the original calculation. It was not foolish to compare insect wings with aircraft wings. In the early 20th century, airplanes were the most successful new example of controlled flight, and researchers naturally borrowed their equations. The failure came from pushing that comparison too far. A model can be mathematically correct and still give the wrong answer if its assumptions do not match the thing being modeled. Enter a bumblebee's wing area, weight and forward speed into equations meant for steady, rigid wings, and the result may say the insect cannot fly. Add rapid flapping, wing rotation, vortex formation, low Reynolds number flow and flexibility, and the missing lift appears without breaking a single physical law. The bumblebee never defeated science. Better measurements, high-speed cameras, smoke trails, and computer simulations allowed science to catch up with the bumblebee. And the famous quote gets the lesson backwards. The insect does not fly because it is ignorant of physics. It flies because every stroke of its wings follows physics with extraordinary precision. The impossible part existed only on a sheet of paper.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!